Good morning everyone, myself Ignorin Mandal, Assistant Professor in Mechanical Engineering Department. Today I am going to present an important topic, combustion in compression ignition engines related to internal combustion engines and automobile engineering. Let's start the session. These are the main contents: combustion in compression ignition engines, comparison of knock in spark ignition engines and compression ignition engines, combustion chambers in compression ignition engines. Basic introduction of compression ignition engines. Combustion in CI engine is quite different from that of an spark ignition engine. While combustion in an spark ignition engine is essentially a flame front moving through a homogeneous mixture, combustion in a CI engine is an unsteady process occurring simultaneously in many spots in a very non-homogeneous mixture controlled by fuel injection. Air intake into the engine is unthrottled, with engine torque and power output controlled by the amount of fuel injected per cycle. Only air is contained in the cylinder during compression stroke, and a much higher compression ratios of 12 to 24 are used in compression ignition engines. In addition to swell and turbulence of the air, a high injection velocity is needed to spread the fuel throughout the cylinder and cause it to mix with the air. Fuel is injected into the cylinders late in the compression stroke by one or more injectors located in each cylinders. Injection time is usually about 20 degree of crankshaft rotation, 15 degree before TDC and 5 degree after TDC. That means top dead center. What are the stages of combustion in compression ignition engines? The combustion in a CI engine is considered to be taking place in 4 stages. Ignition delay period, that contains physical delay and chemical delay. Second one, rapid combustion period or rapid pressure rise. Third stage is controlled combustion period or mechanically controlled period. And last stage is after burning period. Let's discuss one by one. This is a schematic diagram that illustrates the various stages of combustion in a CI engine. First stage is ignition delay period. The ignition delay period is also called the preparatory phase, during which some fuel has already been admitted but has not yet ignited. This period is counted from the start of injection to the point where the pressure time curve separates from the motoring curve, indicated as start of combustion. The delay period in the CI engine exerts a very great influence on both engine design and performance. It is of extreme importance because of its effect on both the combustion rate and knocking, and also its influence on engine starting ability and the presence of smoke in the exhaust. The fuel does not ignite immediately upon injection into the combustion chamber. There is a definite period of inactivity between the time when the first droplet of fuel hits the hot air in the combustion chamber and the time it starts through the actual burning phase. This period is known as the ignition delay period. This figure illustrates pressure time diagram illustrating ignition delay. The delay period is shown on pressure crank angle diagram between points A and B. Point A represents the time of injection and point B represents the time at which the pressure curve that is caused by combustion first separates from the motoring curve. The ignition delay period can be divided into two parts, the physical delay and chemical delay. Let's discuss physical delay and chemical delay. Physical delay. The physical delay is the time between the beginning of injection and the attainment of chemical reaction conditions. During this period, the fuel is atomized, vaporized, mixed with air and raised to its self-ignition temperature. The physical delay depends on the type of fuel, that is, For light fuel, the physical delay is small, while for heavy viscous fuels, the physical delay is high. The physical delay is greatly reduced by using high injection pressures, higher combustion chamber temperatures, and high turbulence to facilitate breakup of the jet and improving evaporation. Chemical delay. During the chemical delay, reactions start slowly and then accelerate until inflammation or ignition takes place. Generally, the chemical delay is larger than the physical delay. However, it depends on the temperature of the surroundings, and at high temperatures, the chemical reactions are faster and the physical delay becomes longer than the chemical delay. It is clear that the ignition lag in the spark ignition engine is essentially equivalent to the chemical delay for the compression ignition engine. In most compression ignition engines, the ignition lag is shorter than the duration of injection. Next stage is period of rapid combustion. The period of rapid combustion, also called the uncontrolled combustion, is that phase in which the pressure rise is rapid. During the delay period, the droplets have had time to spread over a wide area and fresh air is always available around the droplets. Most of the fuel admitted would have evaporated and formed a combustible mixture with air. By this time, the pre-flame reactions would have also been completed. The period of rapid combustion is counted from end of delay period or the beginning of the combustion to the point of maximum pressure on this indicated diagram. The rate of heat release is maximum during this period. It may be noted that the pressure reached during the period of rapid combustion will depend on the duration of the delay period. That is, the longer the delay, the more rapid and higher is the pressure rise, since more fuel would have accumulated in the cylinder during the delay period. Next stage is period of controlled combustion. The rapid combustion period is followed by the third stage, the controlled combustion. The temperature and pressure in the second stage is already quite high. Hence, the fuel droplets injected during the second stage burn faster with reduced ignition delay as soon as they find the necessary oxygen, and any further pressure rise is controlled by the injection rate. The period of controlled combustion is assumed to end at maximum cycle temperature. Last stage is period of afterburning. Combustion does not cease with the completion of the injection process. The unburnt and partially burnt fuel particles left in the combustion chamber start burning as soon as they come into contact with the oxygen. This process continues for a certain duration called the afterburning period. Usually, this period starts from the point of maximum cycle temperature and continues over a part of the expansion stroke. Rate of afterburning depends on the velocity of diffusion and turbulent mixing of unburnt and partially burnt fuel with the air. The duration of the afterburning phase may correspond to 70 degree to 80 degrees of the crank travel from top dead center. These are all about 4 stages of combustion in CI engine. I have discussed ignition delay period, that contains physical delay and chemical delay. I have discussed rapid combustion period or rapid pressure rise. I have discussed controlled combustion period or mechanically controlled period. I have also discussed after burning period. This is the block diagram of combustion in CI engine. The sequence of the events in the entire combustion process in CI engine, including the delay period, is shown in this figure by means of this block diagram. This is for mixture formation, this period is ignition, this is for final combustion, this is the products, and this contains delay period of physical delay and chemical delay. Let's discuss what are the main factors affecting the delay period. That contains compression ratio, engine speed, output, atomization of fuel and duration of injection, injection timing, quality of fuel and intake temperature and pressure. Let's discuss one by one. Compression ratio. The increase in the compression temperature of the air with increase in compression ratio evaluated at the end of the compression stroke is shown in this figure. It is also seen from the same figure that the minimum auto ignition temperature of a fuel decreases due to increased density of the compressed air. This results in a closer contact between the molecules of fuel and oxygen, reducing the time of reaction. The increase in the compression temperature as well as the decrease in the minimum auto ignition temperature decreases the delay period. The peak pressure during the combustion process is only marginally affected by the compression ratio. One of the practical disadvantages of using a very high compression ratio is that the mechanical efficiency tends to decrease due to increase in weight of the reciprocating parts. Therefore, in practice, the engine designers always try to use a lower compression ratio, which helps in easy cold starting and light load running at high speeds. Engine speed. The delay period could be given either in terms of absolute time or in terms of crank angle degrees. This figure shows the decrease in delay period in terms of milliseconds with increase in engine speed in a variable speed operation with a given fuel. With increase in engine speed, the loss of heat during compression decreases, resulting in the rise of both the temperature and pressure of the compressed air, thus reducing the delay period in milliseconds. However, in degrees of crank travel, the delay period increases as the engine operates at a higher RPM. The fuel pump is geared to the engine, and hence the amount of fuel injected during the delay period depends on crank degrees and not on absolute time. Hence, at high speeds, there will be more fuel present in the cylinder to take part in the second stage of uncontrolled combustion, resulting in high rate of pressure rise. Output. With an increase in engine output, the air-fuel ratio decreases, operating temperatures increase, and hence delay period decreases. The rate of pressure rise is unaffected, but the peak pressure reached may be high. Next, atomization and duration of injection. Higher fuel injection press increases the degree of atomization, which reduces ignition delay due to higher surface to volume ratio. Smaller droplets have low depth of penetration due to less momentum. Such droplets may have less velocity relative to air and shorter fuel spray path, where it has to find oxygen after vaporization, affecting air utilization factor. Also, the aggregate area of inflammation after ignition will increase, resulting in higher pressure rise during second stage of combustion. On the other hand, lower injection pressure giving larger droplets give lower pressure rise and smoother running. An optimum group mean diameter of the droplet should be attained with appropriate fuel delivery characteristics. Next, injection timing. The effect of injection advance on the pressure variation is shown in this figure. For 3 injection advance timings of 9 degree, 18 degree and 27 degree before top dead center, the injected quantity of fuel per cycle is constant. As the pressure and temperature at the beginning of injection are lower for higher ignition advance, the delay period increases with increase in injection advance. The optimum angle of injection advance depends on many factors, but generally it is above 20 degree before top dead center. Next, quality of fuel. Self-ignition temperature is the most important property of fuel which affects the delay period. A lower self-ignition temperature results in lower delay period. Fuels with higher Seaton number give lower delay. Other properties of fuel which affect delay period include volatility, latent heat, viscosity and surface tension. This is about quality of fuel. Next, intake temperature. Increase in intake temperature increases the compressed air temperature, resulting in reduced delay period. However, preheating of the charge for this purpose would be undesirable because it would reduce the density of air, reducing the volumetric efficiency and power output. Next, intake pressure. Increase in intake pressure or supercharging reduces the autoignition temperature and hence reduces the delay period. The peak pressure will be higher since the compression pressure will increase with intake pressure. I have discussed intake temperature and pressure. Let's discuss knock in CI engines. In CI engines, the injection process takes place over a definite interval of time. Consequently, as the first few droplets to be injected are passing through the ignition delay period, additional droplets are being injected into the chamber. If the ignition delay of the fuel being injected is short, the first few droplets will commence the actual burning phase in a relatively short time after injection, and a relatively small amount of fuel will be accumulated in the chamber when actual burning commences. As a result, the mass rate of mixture burned will be such as to produce a rate of pressure rise that will exert a smooth force on the piston as shown in this figure. If, on the other hand, the ignition delay is longer, the actual burning of the first few droplets is delayed, and a greater quantity of fuel droplets gets accumulated in the chamber. When the actual burning commences, the additional fuel can cause too rapid a rate of pressure rise as shown in this figure, resulting in a jamming of forces against the piston and rough engine operation. If the ignition delay is quite long, so much fuel can accumulate that the rate of pressure rise is almost instantaneous, as shown in this figure. Such a situation produces the extreme pressure differences and violent gas vibrations known as knocking and is evidenced by audible knock. This phenomena is similar to that in the spark ignition engine. However, in the spark ignition engine, knocking occurs near the end of combustion, whereas in the compression ignition engine, knocking occurs near the beginning of combustion. In order to decrease the tendency of knock, it is necessary to start the actual burning as early as possible after the injection begins. In other words, it is necessary to decrease the ignition delay and thus decrease the amount of fuel present when the actual burning of the first few droplets start. Comparison of knock in spark ignition and CI engines. It may be interesting to note that knocking in SI engines and CI engines is fundamentally due to the auto ignition of the fuel air mixer. In both the cases, the knocking depends on the auto ignition lag of the fuel air mixer, but careful examination of the knocking phenomena in spark ignition and the compression ignition engines reveals the following differences. A comparison of the knocking process in spark ignition and compression ignition engines is shown on the pressure time diagram. In SI engines, the auto ignition of the end gas away from the spark plug, most likely near the end of the combustion, causes knocking. But in CI engines, the auto ignition of the charge causing knocking is at the start of the combustion. It is the first charge that auto ignites and causes knocking in the compression ignition engines. This is illustrated in this figure. It is clear from this figure that explosive auto ignition is more or less over before the peak pressure for the CI engines, but for spark ignition engines, the condition for explosive auto ignition of the end charge is more favorable after the peak pressure. In order to avoid knocking in SI engines, it is necessary to prevent auto ignition of the end gas to take place at all. In CI engine, the earliest possible auto ignition is necessary to avoid knocking. In SI engine, the charge that auto ignites it is homogeneous and therefore intensity of knocking or the rate of pressure rise at explosive auto ignition is likely to be more than that in compression ignition engines. where the fuel and air are not homogeneously mixed, even when explosive autoignition of the charge occurs. Therefore, it is often called detonation in SI engines. In CI engines, only air is compressed during the compression stroke, and the ignition can take place only after fuel is injected just before the top dead center. Thus, there can be no pre-ignition in CI engines as in SI engines. It has already been pointed out that the normal process of combustion in CI engines is by autoignition, and thus normal rate of pressure rise for the first part of the charge for CI engine are higher than those for SI engine in terms of per degree crank rotation, and normally audible knock is always present in CI engine. Thus, when the audible noise becomes severe and causes heavy vibrations in the engine, it is said that the engine is knocking. Therefore, it is also a matter of judgment. A definite demarcation between normal combustion and knocking combustion is very difficult. The rate of pressure rise may be as high as 10 bar per degree crank rotation in CI engines. The factors that tend to increase autoignition, reaction time, and prevent knock in SI engines promote knock in CI engines. Also, a good fuel for spark ignition engine is a poor fuel for CI engines. The spark ignition fuels have high octane rating 80 to 100 and low C10 rating of about 20, whereas diesel fuel have high C10 rating of about 45 to 65 and low octane rating of about 30. This is all about the comparison of knock in SI and CI engines. Let's discuss combustion chambers in CI engines. Direct injection. Entire volume of combustion chamber located in main cylinder where fuel is injected, also called as open combustion chamber. Shallow depth, hemispherical type, cylindrical and toroidal chamber are the main types. Second type is indirect injection. Combustion space is divided into two parts. One part is the main cylinder and other part is the cylinder head. Various types of indirect injection are fuel chamber, compression fuel generated, pre-combustion chamber, combustion fuel induced, and air cell chamber, compression and combustion fuel are induced. Let us discuss one by one. Direct injection type. This type of combustion chamber is also called an open combustion chamber. In this type, the entire volume of the combustion chamber is located in the main cylinder and the fuel is injected into the volume. In direct injection chambers, an open combustion chamber is defined as one in which the combustion space is essentially a single cavity with little restriction from one part of the chamber to the other, and hence with no large difference in pressure between parts of the chamber during the combustion process. There are many designs of open chamber, some of which are shown in these figures. In four-stroke engines with open combustion chambers, induction fuel is obtained either by careful formation of the air intake passages or by masking a portion of the circumference of the inlet valve, whereas in two-stroke engines it is created by suitable form for the inlet ports. These chambers mainly consist of space formed between a flat cylinder head and a cavity in the piston crown in different shapes. The fuel is injected directly into this space. The injector nozzles used for this type of chamber are generally of multi-hole type working at a relatively high pressure. The main advantages of this type of chambers are minimum heat loss during compression because of lower surface area to volume ratio and hence better efficiency. No cold starting problems, fine atomization because of multi-hole nozzle. The main drawbacks of these combustion chambers are high fuel injection pressure required and hence complex design of fuel injection pump. Necessity of accurate metering of fuel by the injection system, particularly for small engines. This is shallow depth chamber. In this chamber, the depth of the cavity provided in the piston is quite small. In heavy spherical chamber, this chamber gives small squeeze. However, the depth to diameter ratio for a cylindrical chamber can be varied to give any desired squeeze to give better performance. This is cylindrical chamber. This design was attempted in recent diesel engines. This is a modification of the cylindrical chamber in the form of a truncated cone with base angle of 30 degree. The swell was produced by masking the valve for nearly 180 degree of circumference. Toroidal chamber. The idea behind this shape is to provide a powerful squeeze along with the air movement similar to that of the familiar smoke ring within the toroidal chamber. Due to the powerful squeeze, the mass needed on inlet valve is small and there is better utilization of oxygen. The cone angle of spray for this type of chamber is 150 degree to 160 degree. Indirect injection chamber or swell chamber. A divided combustion chamber is defined as one in which the combustion space is divided into two or more distinct compartments connected by restricted passages. This is swell chamber. Swell chamber consists of a spherical shaped chamber separated from the engine cylinder and located in the cylinder head. Into this chamber, about 50% of the air is transferred during the compression stroke. A throat connects the chamber to the cylinder which enters the chamber in a tangential direction so that the air coming into this chamber is given a strong rotary movement inside the swell chamber, and after combustion the products rush back into the cylinder through the same throat at much higher velocity. This causes considerable heat loss to the walls of the passage, which can be reduced by employing a heat insulated chamber. This is nozzle, this is globe plug, this is throat, piston, this is spherical shaped swell chamber. However, in this type of combustion chambers, even with a heat insulated passage, the heat loss is greater than that in an open combustion chamber which employs induction swell. This pre-combustion chamber. A typical pre-combustion chamber consists of an antechamber connected to the main chamber through a number of small holes compared to a relatively large passage in the swell chamber. The pre-combustion chamber is located in the cylinder head and its volume accounts for about 40% of the total combustion space. During the compression stroke, the piston forces the air into the pre-combustion chamber. The fuel is injected into the pre-chamber and the combustion is initiated. The resulting pressure rise forces the flaming droplets together with some air and their combustion products to rush out into the main cylinder at high velocity through the small holes. Thus, it creates both strong secondary turbulence and distributes the flaming fuel droplets throughout the air. In the main combustion chamber, where bulk of combustion takes place, about 80% of energy is released in main combustion chamber. This is air cell combustion chamber. In this chamber, the clearance volume is divided into two parts. One is the main cylinder, another is the called energy cell. The energy cell is divided into two parts, major and minor, which are separated from each other and from the main chamber by narrow orifices. This is the two-lobed main combustion chamber, two-part energy cell. This is cylinder head, injector and the cylinder. During compression, the pressure in the main chamber is higher than that inside the energy cell due to restricted passage area between the two at the top dead center. The main advantages of indirect injection combustion chambers are: injection pressure required is low, direction of spraying is not very important. These chambers have the following serious drawbacks which have made its application limited. Those are poor cold starting performance requiring heater plugs. Specific fuel consumption is high because there is a loss of pressure due to air motion through the duct and heat loss due to large heat transfer area. I have already told the comparison between open and indirect combustion chamber. From this table you will be able to understand easily the comparison between open and indirect combustion chamber. From this video lecture you will be able to understand the combustion process in compression ignition engines. If you want to get more videos, please like, share and subscribe my channel. Thank you.